let's take a look at temperature and internal energy. So you probably have a pretty good idea of what is meant when someone says hot or cold or temperature or heat. But we're going to look at it from a physics perspective, which means looking at it in a way that allows us to make sense of what we observe. And to make sense of the observations, the best model we have to do that is the molecular theory. And the molecular theory is the idea that everything is made up of molecules. And yes, molecules are made up of atoms, and atoms are made up of protons and neutrons and electrons. But we're going to think about the molecules. So all everyday objects are made up of these little bits called molecules. And those molecules, according to the molecular theory, are always in constant motion. And they also can interact with nearby molecules through intermolecular bonds. So from that starting place, we can explain a lot. So, for instance, let's move on to the term temperature. I know you know what temperature is. You've heard of it before, you've used it. From a physics perspective, temperature is a measure of the average random kinetic energy per molecule in an object. So if an object has a high temperature, that means that there's a greater average kinetic energy per molecule in that object. So, on average, the molecules in that object are moving around more quickly. They have more kinetic energy on average. If it has a lower temperature, then there's a lower average kinetic energy per molecule in that object. And on average, the molecules are moving around a little slower. They have less kinetic energy per molecule, on average. And it's important to think of that term on average because some of the molecules in an object will be moving faster, some will be moving more slowly. The temperature tells you the average random kinetic energy per molecule. And in the SI system, the unit of temperature is the Kelvin. And yeah, degrees Celsius and degrees Fahrenheit are also seen around the place. We're going to ignore degrees Fahrenheit. I know that's common in the United States. It's not used in most scientific applications. Degrees Celsius is used in scientific applications. But degrees Celsius, a temperature in degrees Celsius, can be either positive or negative. 0 degrees Celsius is set at the freezing point of water in common conditions. Now compare that to Kelvin. The temperature in Kelvin cannot be negative. The Kelvin scale is set up so that 0 Kelvin is absolute zero. And by absolute zero, I mean that that's when the molecules have no kinetic energy and they do not move. So if you imagine a temperature scale, if you have a high temperature in Kelvin, then those molecules have high kinetic energy on average, and they're moving around pretty quickly. And if you lower and lower and lower the temperature, so if you decrease the kinetic energy lower and lower and lower, eventually you'll get to a point where the molecules do not have any kinetic energy. And at that moment, you're at absolute zero. So there's no negative temperature in Kelvin possible, because the kinetic energy can never be less than 0. Kelvin is what's called an absolute temperature scale. It's an absolute temperature scale because its 0 is set at absolute 0. So compare that to degrees Celsius. Degrees Celsius is not an absolute 0 scale because 0 degrees Celsius is not absolute 0. Now let's think about how we can convert between degrees Celsius and Kelvin. To convert, there's just a factor of 273 that's added or subtracted. So the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273. But keep in mind, the unit of a Kelvin and the unit of a degree Celsius is the same size. So a temperature difference in Kelvin is the same as a temperature difference in degrees Celsius. In other words, if I increase the temperature of an object by 1 Kelvin, I have also increased the temperature of the object by 1 degree Celsius. A temperature change is the same in degrees Celsius and Kelvin. Now let's look at 3 terms: internal energy, thermal energy, and heat. And we'll have to be careful with these 3 terms because in the scientific community even, they can be used in different ways. So let's try to be very specific about this. Internal energy refers to the total random kinetic energy of the molecules plus the total potential energy of all of the molecules in an object. Now this is different than temperature. So imagine you have a tiny little block of ice at 0 degrees Celsius and a big block of ice at 0 degrees Celsius. The internal energy is the total random kinetic energy of all the molecules plus the total potential energy of all the molecules in the object. They have the same temperature. They're both at 0 degrees Celsius, but the large block of ice has more internal energy, just because it has more molecules in it. To get the internal energy, you add up all of the random kinetic energies and potential energies of all the molecules. The big block of ice has more molecules, so you're adding more things together. So a large block of ice would have more internal energy than the small block of ice, even though they have the same temperature. Okay. Now, thermal energy refers to a net flow of energy from a high temperature object to a low temperature object. And thermal energy, for our purposes, is going to be synonymous with heat. Thermal energy and heat, for our purposes, will mean the same thing. It's a net flow of energy. So if you had a very hot object next to a cold object, so maybe the hot object is at 500 K and the cold object is at 300 K, well, the thermal energy, or the heat, is the energy that transfers from the hot object to the cold object. And the net flow of energy is always from hot to cold. So, as the energy flows from hot to cold, the hot object is going to lose energy and the cold object is going to gain energy. And after a while, those two objects should reach an equilibrium. The hot object will get cold enough and the cold object will get hot enough that they'll be at the same temperature. So, in this situation, let's say that they both reach a temperature of 400 K. Well, at this moment, we say that those two objects are in thermal equilibrium. Thermal equilibrium because there's no more transfer of energy from hot to cold because there is no more hotter or colder object. There's no net exchange of energy. So thermal equilibrium refers to a situation where the two objects are at the same temperature and there is no more net flow of thermal energy between them. Okay, now let's shift gears. Let's think about how different materials respond to an amount of thermal energy that's added to them. So, to start with this, we're going to consider this idea of a specific heat capacity. Specific heat capacity is defined as the energy necessary to increase the temperature of 1 kilogram of substance by 1 Kelvin, or by 1 degree Celsius. Because remember, we're talking about a temperature change, and a temperature change in Kelvin is the same as a temperature change in degrees Celsius. And if we write down the specific heat capacity as an equation, well, specific heat capacity is usually represented with the letter lowercase c. C is equal to Q divided by M delta T. And if we rearrange that, we can get Q is equal to MC delta T. Now let's define all this stuff. In these equations, Q represents the energy transferred to the object. Okay, Q is the energy transferred to the object. It's the thermal energy that's passing into the object. M represents the mass of the object, and delta T represents the temperature change of the object. All right. From this first equation, we can get the units of specific heat capacity. The units are the units of energy divided by the units of mass divided by the units of temperature change. So, joules per kilogram Kelvin. Or it can also be written as joules per kilogram degrees Celsius. That would be the same thing. And let's try to use these equations to make a little sense of this. So let's start out with Q is equal to MC delta T. Consider a situation where you just have an object, and you're going to keep the same object the whole time. And in two situations, you're going to have, well, in one situation you'll have a big temperature change, and in one situation you'll have a small temperature change. In both situations, M and C are the same, right? Same object, so it has the same mass, same specific heat capacity. In the object where you have a larger change in temperature, think about what that means about Q. Well, if delta T is big, then that means Q has to be bigger. So you probably could figure this out, but if you have a larger temperature change, that's going to require more heat, more thermal energy to be added to the object. Okay. Now let's go over to this C is equal to Q over M delta T equation. Well, let's see. Let's think of two situations. Let's think of a situation where you have the same mass and you have the same temperature change, but you have two different materials. And let's say the material on the left has a high specific heat capacity, and the temperature on the right has a low specific heat capacity. Well, if your specific heat capacity is large, then that means for a certain temperature change, you have to have a larger Q. You have to add more heat to it to get that temperature change. And over here on the right, if you have a small specific heat capacity, then for a certain change in temperature, you need smaller Q. You have less heat is necessary to do that. So another way to say this, water. Water is a substance with a pretty high specific heat capacity. And what that means is it takes a lot of heat, relatively, to change the temperature of water. Now we'll compare that to aluminum. Aluminum has a pretty low specific heat capacity. So aluminum, it requires relatively small amount of heat to change the temperature of aluminum by a certain amount. So that gives us another kind of more intuitive way of thinking about specific heat capacity. It is a measure of how much heat is necessary to change the temperature of a certain substance.